Hello students, in this video we are going to discuss Kirchhoff's laws for electrical networks. Why we are introducing Kirchhoff's laws or rules means whenever the circuit is complicated to solve, to find the net resistance or current or potential between any 2 points, it is not easy in normal methods. In this case we'll go for Kirchhoff's laws. There are two laws or rules here. One is Kirchhoff's first rule. It is also called as junction rule, or it is also called as Kirchhoff's current law, KCL. According to this Kirchhoff's first law, the algebraic sum of the currents meeting at any junction is 0. Mathematically, we can write summation I is equal to 0. Here we will follow one sign convention. What is that? Incoming currents are taken as positive and outgoing currents are taken as negative at a given junction. You are aware of junction, I think so. Suppose say here there are few wires are meeting at a point. So this point where all the wires are meeting is nothing but called as junction. We are naming it O. Suppose say I1 current is entering the junction, I2 current also entering the junction, I3 is coming out, I4 is coming out, suppose say I5 is entering. So according to this one, the currents which are entering, that means incoming currents are taken as positive. So we can take I1 is positive, here I2 is positive according to the diagram, and I3 is negative, and I4 also negative, but I5 is positive. That is equal to 0. This is as per the statement. And we can reframe this statement, we can reframe this equation as I1 plus I2 plus I5 is equal to I3 plus I4. This I1, I2, I5 are entering the junction. I3 and I4 are leaving the junction. Based on this one, we can give one more statement which is called as Kirchhoff's first rule only. In a circuit at any junction, the sum of the currents entering the junction must equal to the sum of the currents leaving the junction. One more statement also we can give it. And whatever the currents are entering, the sum of the currents entering should be is equal to the sum of the currents leaving, means it is following one of the law called law of conservation of charge. This law is based on the conservation of charge. That means whatever the charge is entering, the same amount of charge is leaving. This is first law of Kirchhoff's. And we will discuss one illustration or example based on this one. Figure shows three resistances are connected with the switch S. Initially, the switch is open. When the switch is closed, find the current passed through the junction. Current passed through the switch. Here, according to this data, the diagram is like this. It is one of the resistor. Here also one more resistor. Assume that it is point A and B. And at point A, the potential is 20 volt. The resistance is 2 ohm. At point B, the potential is 5 volt. And the resistance is 4 ohm. And from here one more resistance is taken, and there is a switch which is in open initially, and finally other end is connected to the earth. This is the switch, and this resistance also 2 ohm. This is the diagram based on the question given. Now, when the switch is closed, what will happen? I am taking this one like this. The switch is closed here. 20 volt, 2 ohm, 4 ohm and 5 volt at B, and it is 2 ohm. The switch is closed. When the switch is closed here, the current will pass through switch as well as 2 ohm resistor, and this earthing means its potential will be 0 volt, and we can take this common point here V and assume that the current is passing from 20 volt is I1 and from 5 volt is suppose say I2 at point V. Both will combine together and passing through the switch is I3. So here we are discussing the application or illustration based on Kirchhoff's current law. So according to this one, from Kirchhoff's current law, I1 plus I2 is equal to I3. But we don't know I1 and I2 values. So what we will write here, we will write in terms of currents, in terms of voltages and resistances. I1 can be written as 20 minus V divided by 2. I2 can be written as 5 minus V divided by 4, that is equal to 2 minus 0 divided by 2. Why I am writing 20 minus V instead of V minus 20 means 20 value will be generally higher than V. So, after further simplification by taking 4 is LCM and sending towards right, and you can get it is 40 minus 2V plus 40 minus 2V plus 5 minus V is equal to, we will have here I3 is nothing but it is nothing but V minus 0 by 2, that is equal to 2V, we will get it. And after this we will have 5V is equal to 45, from this V is equal to 9 volt. So this is the V value, but we need the current passing through the switch, that means I3 value we need. We can write I3 is nothing but V minus 0 by 2. V value is nothing but 9 by 2, that is nothing but is equal to 4.5 ampere. So this is the current passing through the switch. It is one of the illustration based on Kirchhoff's first rule. Coming to Kirchhoff's second rule. What Kirchhoff's second rule says, it says about the loop, it will say about the voltage. That's why Kirchhoff's second law is also called as Kirchhoff's loop rule, or it is also called as voltage law, Kirchhoff's voltage law, KVL. How can we define this? Means the algebraic sum of the changes in potential around any closed loop involving resistors and cells in the loop is 0. Mathematically, we can write delta V, summation of delta V is equal to 0. And this law is based on conservation of energy. Okay. So before going to the illustration and detailed explanation, we'll go through some sign conventions. We can take any direction as the direction of traversal, means to travel. It may be the clockwise direction or anti-clockwise direction, that is based on the interest of the student. The EMF of a cell is taken as positive if the direction of traversal is from its negative to positive terminal. That means if you are taking this is a cell, negative and positive terminal, if we are traveling from negative to positive terminal through electrolyte, assume that it is point A is connected to negative terminal, point B is connected to positive terminal. We are moving from A to B through electrolyte. So, potential at B will be higher than potential at A because B is connected to positive, A is connected to negative. So, potential difference or change in potential can be taken as final potential VB minus initial potential Y, means we are moving from A to B. For us, A is initial, B is final. That value can be taken as E, that is positive value. Coming to the point 3. The EMF of the cell is taken as negative if the direction of the traversal is from its positive to negative terminal. That means we are taking the same cell. It is point A and it is point B, but we are moving from positive to negative terminal. In this case, the initial point is B, potential VB. The final point is A, potential VA. So, potential difference in this case will be VA minus VB, generally final value minus initial value. That is equal to minus of E. This sign convention we need to follow. And fourth one, the current resistance product, that is IR, is taken as negative if the resistor is traversed in the same direction of assumed current. Assume that this is a resistor through which current I is passing, its resistance is R, current is moving from A to B, and we are traveling from A to B. So, the resistor is traversed in the same direction of the current. Then what is the value of change in potential? Change in potential means final potential at B minus potential at A. For us, B will be the final point where the final potential is VB. Point A is initial potential point and the potential is VA. VB minus VA is equal to I into R. This value is negative. The reason is the final actual current is moving from A to B, means A is at higher potential, B is at lower potential. Current travels from higher to lower potential. So, lower potential minus higher potential will be negative value. So, the potential difference is negative minus IR. Be careful. This sign convention I am taking based on summation delta V is equal to 0. Somebody will take summation E is equal to summation IR. They may take it opposite, but both are correct only. And fifth one, the current resistance product IR is taken as positive. The resistor is traversed in the opposite direction of assumed current. So, we are taking the same, this is a resistor of resistance R through which current I is flowing from point A to point B, but we are moving in the opposite direction of the current. That means from B to A. For us, B is the initial point, A is the final point, potential at B is initial potential, potential at V is final, A is final potential. So, the potential difference means VA minus VB, that is equal to VA is more than VB because the current is moving from A to B. So, then automatically the potential difference will be IR plus IR if you want. And if you are applying the same for capacitors, for even capacitors, if we are moving from positive to negative terminal, so this is A, suppose say this is B, the potential difference is VB minus VA, always final minus initial. For us it is final, B initial is A. That is equal to, from capacitance concept we have studied, potential difference is equal to charge per capacitance. Here it is VB minus VA means VB is lower, VA is higher. Lower minus higher will be negative. Now, suppose say the same thing we are taking, the direction is opposite. It is A and it is B, positive and negative. We are moving from negative to positive plate. Then the potential difference will be final potential, means potential at A minus potential at B. That is nothing but plus Q by C. So these are the sign conventions we need to use to apply Kirchhoff rules. It is one of the most important concepts for CBSE, for any other competitive examination. We may expect the questions from this topic. That's why especially I am focusing on this. One illustration based on this. A battery of 10 volt and a negligible internal resistance is connected across the diagonally opposite corner of cubical network consisting of 12 resistors, each of resistance 1 ohm as shown in figure. Determine the equivalent resistance of the network and current along each edge. Okay. Now, according to the given data, we have E value is equal to 10 volt and the resistance of each one is 1 ohm. We need to find out R equivalent diagonally for this given figure and current passing through each edge we need to. And the resistance for each edge we are assuming that R. Later we can substitute the value of R. Now, from this cell of EMF E, 3I current is released. You can take 6I also, you can take 9I also, you can take I also, choice is yours. For my convenience, I am taking 3I because at junction A, this 3I will be split into 3 equal parts. So that is I across AB, I across AD, I across A dash. And after reaching B, again this I is splitting into I by 2, from B to C, from B to B dash. Similarly, from D to C and D to D dash, I by 2, I by 2. From A dash to D dash, A dash to B dash, I by 2, I by 2. But finally at C dash, at C, I by 2 will combine, will get I value. At B dash will get I by 2 plus I by 2 I from Kirchhoff's first rule. At D dash will get I by 2 plus I by 2 I. So D dash to C dash is I, B dash to C dash is I, C to C dash is I. By combinedly at C dash will get 3I. So according to this one, if you apply Kirchhoff's voltage rule for the loop A, B, C, C dash, E, A, closed loop, what we can get? Current passing through A to B is I through resistance R. So the potential difference will be minus IR as per the rule. From B to C, I by 2 is there, minus I by 2 into R or IR by 2. From C to C dash, again minus IR. And we are moving from negative to positive terminal of the cell. So it will be positive E is equal to 0. From this we can write 5 minus 5 IR by 2 is equal to minus E. Therefore, E is equal to 5 by 2 times of IR. We can take it as equation number 1. But for complete circuit, the E value is equal to I total, that means I equivalent into R equivalent. So I total is nothing but 3I, R equivalent we have to find out. You can take it as equation number 2. From this, equation number 1 and 2 both are same. Therefore, 3I R equivalent is equal to 5 by 2 IR. I will be get cancelled here. R equivalent is equal to 5 by 6 times of R. It is general expression for a cube which has the resistance R as its edge diagonally. Now we know as R is equal to 1 ohm is given, R equivalent diagonally is nothing but 5 by 6 ohm. This is one of the answer to us. One more thing is current across each edge. So we can use either equation number 1 or equation number 2. Suppose say if you are writing equation number 1, from this E value is given as 10 volt, that is 5 by 2 into I, R value is nothing but 1. From this I is equal to 20 divided by 5, that is nothing but 4 ampere. That means the current between A to B, A to D, A to A dash is nothing but 4 ampere. That means current across AB, across AD, across A dash, that is also nothing but across B dash, C dash, that is across C dash, I across D dash, C dash is nothing but 4 ampere. Now the current across BC, that is nothing but I by 2, current across DC, the current across A dash D, current across D dash, current across A dash B dash, current across B dash, is equal to I by 2, that is nothing but 2 ampere. Remaining terms, if there is anything missed, please check. And for complete circuit, the current coming from the cell is 3I, that is nothing but 3 into 4, that is 12 ampere. So this is the answer for the illustration based on Kirchhoff rules. And Wheatstone bridge also will be working based on the Kirchhoff rule. We can derive it based on Kirchhoff rule. Already the video is done. You can go through current electricity chapter. Thank you. Till now, if you did not subscribe, please subscribe. I hope the concept is clear. If further any topics you need, please text the comment box. This topic is one of the most important topic for the exams. Thank you.